Welcome to Quick Particulars. Have you ever wondered what it takes to launch a rocket into space? Join us on an exhilarating journey as we delve into the captivating world of rocket science and explore the science behind rocket launches. Rocket launches represent a remarkable feat of engineering and scientific understanding. They involve complex processes and principles from various scientific disciplines. This video explores the science behind rocket launches, highlighting key concepts and stages involved in propelling a rocket into space. Newton's laws of motion. Rocket launches rely heavily on Newton's three laws of motion. A. Newton's first law of motion, law of inertia: an object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by an external force. Before launch, a rocket remains stationary on the launch pad until sufficient force is applied to overcome inertia. B. Newton's second law of motion, law of acceleration. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Rockets experience a significant force called thrust, generated by the combustion of propellants in the rocket engines. The force of thrust propels the rocket forward, overcoming gravity and air resistance. C. Newton's third law of motion, law of action-reaction. For every action, there is an equal and opposite reaction. The rocket engines expel gases at high velocities, creating a force in one direction, action, that results in an equal and opposite force propelling the rocket upward, reaction. Propulsion systems. Rocket propulsion systems play a critical role in launching rockets. There are two main types. A. Liquid rocket engines. Liquid rockets use liquid propellants, typically liquid oxygen, LOX, as the oxidizer and liquid hydrogen, LH2, as the fuel. These propellants are pumped into a combustion chamber, where they mix and ignite to produce high-pressure and high-temperature gases. The expansion of these gases through a nozzle creates a high-velocity exhaust jet, generating thrust. Liquid rockets offer precise control over the engine's performance. B. Solid rocket motors. Solid rocket motors, SRMs, use a solid mixture of fuel and oxidizer, known as the propellant grain. Once ignited, the propellant burns in a controlled manner, producing a high volume of hot gases. The exhaust gases are expelled through a nozzle, generating thrust. Solid rocket motors provide high thrust levels but are non-restartable and offer limited control over the propulsion. Orbital mechanics. The launch trajectory and achieving orbit involve several principles of orbital mechanics. A. Escape velocity. To reach space, a rocket must achieve a speed known as escape velocity, which is the minimum velocity required to escape Earth's gravitational pull. The escape velocity depends on the mass and radius of the planet. For Earth, it is approximately 40,270 kilometers per hour, 25,020 miles per hour. B. Velocity and altitude. During launch, rockets ascend vertically, gradually tilting their trajectory to gain horizontal velocity. This process, known as a gravity turn, helps conserve propellant by taking advantage of Earth's rotation. As the rocket gains altitude, it accelerates horizontally, reaching orbital velocity, around 28,000 kilometers per hour or 17,500 miles per hour for low Earth orbit. C. Orbital insertion. Once the desired velocity is achieved, the rocket's upper stage performs a burn called the orbital insertion maneuver. This maneuver allows the rocket to enter and stabilize in a specific orbit around Earth. Aerodynamics and atmospheric effects. Rocket launches must account for aerodynamic forces and atmospheric effects. A. Drag. As the rocket ascends through the atmosphere, it encounters air resistance or drag. Streamlining the rocket's shape minimizes drag, allowing it to move more efficiently through the air. B. Max Q. Max Q, maximum dynamic pressure, is the point during ascent when aerodynamic forces on the rocket are at their peak. Rockets are designed to withstand these high forces, and the thrust is usually reduced momentarily to minimize structural stress. Guidance, navigation, and control, GNC. GNC systems play a vital role in rocket launches. A. Guidance. Guidance systems use sensors, such as inertial measurement units, IMUs, and GPS, to determine the rocket's position, velocity, and attitude. They provide the necessary information to steer the rocket along the desired trajectory. B. Navigation. Navigation systems process data from various sensors to determine the rocket's precise location and trajectory during flight. This information helps ensure the rocket follows the intended path accurately. C. Control. Control systems use actuators, such as gimbaled engines or thrusters, to adjust the rocket's orientation and maintain stability. They counteract external disturbances and keep the rocket on its intended trajectory. Conclusion. Rocket launches are a fascinating demonstration of scientific principles, engineering expertise, and technological advancements. From Newton's laws of motion to propulsion systems, orbital mechanics, and GNC systems, a deep understanding of various scientific disciplines is essential for the successful launch of a rocket into space. By continually pushing the boundaries of scientific knowledge, we expand our understanding of the universe and pave the way for further space exploration. Thanks for watching.